Welcome back to the test review for part 3. We'll do a couple more problems here. One of the reasons I cut these up in shorter segments, it's a lot easier to download them that way, so if you're wondering why. Alright, so we got number 6. What's the mass of SO2? Sulfur dioxide was used up in the reaction with an excess of oxygen gas if 12.4 grams of sulfur trioxide is formed. And they actually give us the problem, or the equation here, so I'll just write it down. So SO2, yep, that's O2, yep, goes to 2SO3. And those are all molecular, so we don't need to worry about charges or anything. And we have 12.4 grams of SO3. Alright, going to pull this out so I can work on the problem here. And let's go ahead and work on this. Alright, can't use grams, so right away we got to convert grams to moles. We got 1, and we know in 1 mole of SO3 it's 80.1 grams of SO3. So that we can go ahead and do the math real quick, clear that one out. 12.4 divided by 80.1, and that is 0.155. So we have 0.155 moles of SO3. Alright, so now we need so that's how many moles we have for a coefficient of 2. We want to see how many we have for 1. So 0.15, oops, I should go the other way. So we have coefficient of 2 gives us 0.155, and we want to know what x is. If you wanted to go the other way, put the number of moles divided by the coefficient. You can do that. I just like doing it this way. So it's 0.155. And so the next thing we need to do on here is go ahead and let's divide that out. So x equals 0.155 divided by 2 is 0.078. 0.078. Alright, so that's what we got. Alright, let's go through and do this now. So our before, our change, and our after. Well, we know, so there's the coefficient of 2. Well, this one happens to be 2 also, and this is what we were given. So we know that is going to be, or you can think of it 2 times that, if you will. So that's going to be 0.155. They actually tell us the oxygen is in excess. The change is, and then we don't make anything yet. So let's go ahead and do the change. We're going to use all of this up. And we're actually going to use for the oxygen, we're really only going to use that. Coefficient of 1 times that. We're going to use that. And then we are going to make, we've already got the number of moles here. So we are going to make 0.155. Alright, it's going to get used up. This is an excess, and we end up with 0.155. So we want to know how much sulfur trioxide is formed here. And we can go ahead and let's go ahead and find out what we got. We want to know the grams. Now we've got the moles. So 0.155 moles of SO3 is formed. And we need to go ahead and get the molecular mass. And let's see. Oh, excuse me. We want the mass of SO2 here. My fault. We want to know the what mass of SO2 is used up. So let's just change that to a 2. My fault on that. So 1 mole of sulfur dioxide. So we want sulfur dioxide is 64.1 grams of sulfur dioxide. And that produces, let me bring this down here. Go ahead and do that. 0.155 times 64.1 equals 9.94 grams of sulfur dioxide. So that's what we have there. So there's problem, and this was problem number 6. Alright, let's get rid of this one, and let's look at problem number 7. Problem number 7, I threw up percent yield in here. The reaction between 15.8 grams of ammonia and excess oxygen gas produces 21.8 grams of NO gas and some water. Determine the percent yield. Alright, so let's go ahead and do that. So the reaction between NH3 and excess oxygen produces nitrogen monoxide, and some water. And we have 15, let's just write some things down here. We've got 15.8 grams of NH3, and it produces 21.8 grams of NO. Well, it produces this, so this is probably going to be our actual yield. And we want to determine percent, so we need to find out the theoretical yield that gets produced. Alright, so this. So, next thing we need to do, we've got this, but as usual, we need to go ahead and balance the equation. Let's leave oxygens for last. And so, nitrogen looks pretty good. 3 hydrogen, 2 hydrogen, LCD is going to be 6. So let's go ahead and just do it right off the bat. 2 nitrogen is going to be 2 there. So now, again, always leave the oxygens to last. So we have 2 times 1 is 2, 3 times 1 is 3, that's 5. So what times 2 is going to give me 5? 2.5. Well, we can't use that, so we've got to go ahead and double everything. So I'm just going to rewrite this. So 4 ammonia plus 5 oxygen will give us 4 nitrogen monoxide plus 6 water. Alright, so now we've got our balance. Alright, so we are given 15.8 grams of ammonia, or NH3. Well, we know we can't use that, so we got to go ahead and convert that to moles. And I'm going to do it down here. I'll give myself some room down here to do it. So 15.8 grams of NH3 over 1. And I'll probably end up bringing this down here. We know, let's give myself some room. We know 1 mole of NH3. A mole of NH3 is 17 grams of NH3. So if we go ahead and do the math, that's pretty close to 1. That's going to end up being 0.1 0.929 moles, get those going, of NH3. Alright, so that's how much we have for really 4 moles. So 4 moles, the coefficient of 4 gives us this much. Well, we want to find out what 1 would be worth. And again, we'll just go through and do that ratio. 4x equals, oops, one step ahead of myself. So 4, pull this up a little bit, over 0.929 equals 1 over x. Push that up a little bit. Same thing we've done before. 4x equals 0.929. So what does x equal? X equals 0.929 divided by 4, 0.232. 0.232. Alright, so that's what 1 will equal. Alright, so we've got that now. We can go back and, just like the other problems we did, we can go back and start crunching this out. So the before, the change, and the after. Well, we know we get nothing here when we do this. Alright, so the before, we know how much ammonia we got. We got 0.929. So we'll put that in there. 0.929. We have excess oxygen. The problem said that. And we don't know how much of that we have yet. Alright. So the change, we're going to lose all this, 0.929. Kind of interesting to note here. If we were to go ahead, we have coefficient of 5. So 5 times 0.232, we actually are going to use up 1.16 moles, but we know that's in excess. And let's just finish this off. This is going to be 0 also. But that's in excess. Doesn't matter. We had plenty of this, and we used that much. Next step is, well, how about our products? Coefficient of 4. So 4 times this value is going to end up being 0.929. So that's how much we're going to get. And actually, we get quite a bit of water. So 6 times 0.232 is 1.39. So 1.39. So there's our molar ratios, if you will, for the completed reaction once it goes to completion. Alright, so now we know we get 21.8 grams of nitrogen monoxide. So that is what we're getting. So we need to find out, if this is the actual, we need to find out what the theoretical is. So we need to take this value, and we need to take that value and convert it to moles. Or excuse me, to grams. So 0.929 moles of NO over 1. And we know there are 30 grams of NO and 1 mole of nitrogen monoxide. So that equals 27.9 grams of nitrogen monoxide. Alright, so this is our theoretical. Well, we need to take the actual, this is what we actually got, divide by the theoretical, multiply by 100. Very easily, we can go 21.8 divided 27.9 times 100 will give you 78%. So there's what we have on this particular problem, and we'll stop this one and we'll come back and do some more.